NASA has confirmed something that should be impossible. 3I/ATLAS, the mysterious interstellar visitor that's been defying physics since we discovered it, is not leaving. It's staying in our solar system permanently. This wasn't supposed to happen. Interstellar objects follow hyperbolic trajectories. They swing past the sun and slingshot back out into deep space. That's what Oumuamua did. That's what every comet and asteroid from beyond our solar system should do. But Atlas has done something no natural object should be capable of. It's bled off enough velocity to become gravitationally bound to our sun. The energy requirements to accomplish this are staggering. We're talking about slowing down from 130,000 miles per hour to orbital velocity, a deceleration that would require either years of continuous rocket thrust or gravitational maneuvers. So precise they border on impossible. The thing nobody tells you is that objects don't just decide to stay. They don't break themselves into permanent orbits unless something is actively controlling them. And NASA's announcement, buried in technical language and careful phrasing, essentially confirms what many scientists have been afraid to say out loud. We're not dealing with a comet anymore. We're dealing with something that just parked itself in our cosmic neighborhood, and it's not leaving. If you want to stay updated on what happens next with Atlas, hit that subscribe button and turn on notifications, because this story is far from over. The announcement came during what was supposed to be a routine orbital mechanics briefing. A lead NASA astrophysicist stood before a room of reporters and delivered news that fundamentally changes humanity's relationship with the cosmos. Based on 3 months of continuous tracking data, we can now confirm that 3I Atlas has achieved stable orbital insertion around our sun. The object's current trajectory indicates a highly elliptical orbit with a period of approximately 127 years, placing it permanently within our solar system. The room went silent. Then the question started, how is this possible? What mechanism could cause an interstellar object to slow down enough to be captured? Has anything like this ever been observed before? The NASA representatives' answers were carefully measured. We're still analyzing the data to understand the exact mechanisms involved. There are several theoretical possibilities we're exploring. This represents an unprecedented opportunity for long-term study of an extrasolar object. What they didn't say was far more important than what they did. No mention of propulsion, no discussion of the impossible energy requirements, no acknowledgement that every orbital mechanics model says this shouldn't happen naturally. A senior astronomer who attended the briefing described the atmosphere. Everyone in that room understood the implications. This wasn't a scientific update. It was NASA telling us as carefully as possible that something artificial just took up residence in our solar system. The technical language was diplomatic cover for a reality none of us were prepared to accept. The orbital parameters NASA released tell the story. Atlas's new orbit takes it from just inside Earth's orbital path out to the asteroid belt and back. At its closest approach, it will pass within 15 million miles of Earth, close enough for detailed observation with even modest telescopes. At its most distant point, it will venture out past Mars before returning. That's not a random capture orbit. That's a surveillance orbit designed to provide optimal observation of the inner solar system while maintaining a relatively safe distance from the sun's intense radiation. To understand why NASA's announcement is so shocking, you need to understand the physics of what just happened. And those physics point in only one direction: deliberate action. Interstellar objects enter our solar system with what's called hyperbolic excess velocity. They're moving so fast that the sun's gravity can't capture them. Think of it like throwing a ball. Throw it too fast and it escapes Earth's gravity entirely. That's what hyperbolic velocity means. Oumuamua entered our solar system at about 87,000 miles per hour. It swung around the sun, picked up speed from the gravitational assist, and shot back out into interstellar space at nearly 200,000 miles per hour. That's what's supposed to happen. Atlas entered at roughly 130,000 miles per hour to become captured. To slow down enough that the sun's gravity can hold it permanently, it would need to lose approximately 70,000 miles per hour of velocity. That's an enormous energy dissipation. A JPL orbital mechanics specialist explained the impossibility. To lose that much velocity naturally, Atlas would need to either collide with something massive, which would destroy it, or perform multiple gravitational assists past planets in exactly the right sequence. We've mapped its trajectory. It didn't do that. It slowed down continuously over several months, which requires constant thrust. No natural mechanism can provide that. The deceleration pattern NASA recorded shows something even stranger. Instead of slowing down smoothly, Atlas decreased velocity in steps, periods of steady deceleration followed by coasting phases. That's exactly how you'd expect a spacecraft with limited fuel to behave, burning engines in bursts to conserve resources. Natural objects don't have fuel. Natural objects don't manage their deceleration in optimized patterns. And natural objects definitely don't execute the kind of precision maneuvers required to insert into a stable orbit on the first try. A propulsion engineer analyzing the data calculated what would be required to accomplish what Atlas did would require a rocket engine capable of continuous operation for months, carrying fuel equal to roughly 40% of the object's total mass. We're talking about technology decades beyond our current capabilities. And that's assuming conventional propulsion. If they're using something more exotic, ion drives, nuclear engines, or physics we don't understand, the implications are even more staggering. The specific orbit Atlas has settled into isn't random. When you analyze the parameters, the inclination, the eccentricity, the perihelion, and aphelion distances, a clear pattern emerges. This orbit was chosen for specific strategic purposes. The 127-year orbital period means Atlas completes one full circuit of its path, roughly twice per average human lifetime. That's long enough to observe multiple generations of human development, but short enough to return regularly for updated intelligence. The orbital inclination is nearly zero. It orbits in the same plane as Earth and the other inner planets. That's the optimal configuration for monitoring planetary activity. An inclined orbit would spend significant time above or below the ecliptic plane where observation angles are poor. Atlas chose the surveillance sweet spot. A military space analyst described the implications. If I were tasking a reconnaissance satellite to monitor the inner solar system, this is exactly the orbit I'd choose. Close passes by Earth for detailed observation, extended time in the asteroid belt where you're difficult to track, and a trajectory that provides line-of-sight access to all the inner planets at various points in the cycle. The perihelion, closest approach to the Sun, occurs at a distance that's just outside Earth's orbit. That placement is strategic for two reasons. First, it means Atlas will never experience the extreme solar heating that causes natural comets to disintegrate. Second, it ensures regular close approaches to Earth without the object ever entering the planet's hill sphere, where Earth's gravity would dominate and potentially capture it. But here's what's really unsettling. The orbit NASA describes includes regular alignment windows with Earth. Every 11 years, Atlas returns to approximately the same position relative to our planet. That's not a short-term coincidence. That's built-in resonance designed to maintain consistent observation opportunities over centuries. An orbital dynamics researcher mapped out the future positions. Over the next several hundred years, ATLAS will pass through specific zones in its orbit that align with Earth's position in predictable patterns.